All right, let's jump right in. We live in a world that is just flooded with scientific research, right? So here's a huge question. How do we actually figure out what's important? How do we find the real breakthroughs in all that noise? Well, today we're going to get into the science of how we measure science itself. Seriously, just take a second and think about that. If you had to measure a scientist's impact, how would you even start? It's a puzzle that universities, funding agencies, and honestly, even scientists themselves are trying to solve every single day. And the answer, it's not nearly as simple as you might think. For a long, long time, the easy answer was just count the number of papers a researcher published. Simple. More papers mean more impact, right? Well, not so fast. The real answer, as we're about to find out, is way more complex and frankly, a whole lot more fascinating. To get to that real answer, we need to step into this pretty specialized field. It's literally the science of measuring science. And it's got a name, bibliometric analysis. So what on earth is that? Okay, that sounds a little academic, but here's the bottom line. Bibliometric analysis is all about using data, tons of data, to understand the world of research. It's how big institutions and policymakers figure out who's productive, spot the next big thing, and make smart decisions about where to invest their time and money. I think the best way to picture it is like this. Imagine you're creating a giant, detailed map of the entire scientific world. But instead of showing cities and roads, this map shows you research papers, authors, and ideas, and, this is the crucial part, how they're all connected to each other. So let's circle back to that easy answer, just counting papers. This is where we hit a really big wall, because this super simple approach, it is shockingly common. Get this. A recent analysis found that a staggering 85% of studies that try to measure an author's performance look only at their number of publications. That means the huge majority of them are using a metric that completely ignores the quality or the actual influence of the work. And you might think, well, what about some of the fancier metrics? Even more advanced ones, like the H-index we're about to talk about, have their own issues. They can get thrown off by a single paper that goes viral, and they can be really unfair to talented researchers who are just starting their careers. The main takeaway here is that there's no single magic number. What we really need is a whole toolkit. And the good news is that toolkit exists. We can absolutely move beyond just counting papers and start using much smarter metrics to get a way clearer picture of a researcher's true impact. So let's talk about that H-index. Now, like we said, it's not perfect, but it is a massive step up from just counting papers. It tries to measure two things at once: productivity, which is the number of papers, and the citation impact of those papers. So, for example, if you have an H-index of 10, it means you've published 10 papers that have each been cited at least 10 times. Here's a great analogy. Just counting papers is like counting how many times a baseball player steps up to the plate. That's it. But the H-index is more like rewarding them for both consistently getting hits and for hitting those massive, game-changing home runs. See the difference? It's about that balance between quantity and quality. And what's really cool is that the H-index is just the beginning. There are other tools in the kit too. You've got the G-index, which gives even more weight to those home run papers. It's all about recognizing the biggest, most influential work. And then there's the M-index, which is brilliant. It fixes that problem we mentioned earlier by dividing the H-index by the number of years someone's been researching. It's a much, much fairer way to look at up-and-coming talent. But hey, measuring science isn't just about ranking people. Not at all. It's also about mapping the entire universe of ideas. Some of the most powerful tools out there let us literally see how different research topics are connected and how they change over time. One of the key techniques for doing this is called co-word analysis. Basically, this method scans a gigantic collection of papers and looks at how often different keywords show up together. So if gene therapy and cancer are constantly appearing in the same articles, co-word analysis flags that and says, hey, there's a really strong connection here. So how does it actually do that? Well, you can break it down into 4 simple steps. First, you pull all the keywords from thousands of papers. Second, you analyze how often pairs of those keywords appear together. Third, you use software to draw a network map of all those connections. And finally, this is the cool part. You look for groups of tightly connected keywords. We call those clusters. And those clusters, that's where the magic really happens. Each cluster represents a distinct theme or a specific subfield within the broader topic. It's like we're discovering different neighborhoods on our map of science, showing us the major areas of focus in a field and how they all fit together. And cohort analysis isn't the only mapping tool. There's also something called bibliographic coupling. This connects papers that use the same references, which tells us who's building their research on the same foundation. Then you have co-citation analysis. This links two older papers together whenever a new paper cites them both, revealing which classic ideas are now being seen as intellectually connected. Each tool gives us a totally different view of the hidden architecture of a scientific field. Okay, so we've got smarter ways to evaluate researchers and these incredible tools to map ideas. But why does any of this really matter? Why should we care so much about measuring science better? Because it lets us finally see the big picture. With these tools, we can spot emerging trends and new research frontiers way before they hit the mainstream. We can make much smarter, data-driven decisions about which projects actually deserve funding. We can see these beautiful, complex global collaboration networks and understand how knowledge actually flows around the planet. And maybe most importantly, we can get past those lazy, simple metrics and truly appreciate the complex, nuanced impact of scientific work. And that brings us to one last big idea to chew on. If we have a better, more accurate map of the entire scientific world, a map that shows us the most promising avenues, the hot new frontiers, the best people to collaborate with, could we actually use that map to speed up the pace of discovery itself? Something to think about. Thanks so much for tuning in.